While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
The recent COVID epidemic has triggered several different crises that are testing our civilization's potential for both coordination and cooperation. Data about infection rates and their growth has been the main source for public discussion and has inspired many visualization works. We propose a VA approach that incorporates a growth predictive model. This allows the correlation monitoring of the virus population development. We also can relate it to different government response events, as well as identify key dates.
In a visualization, laying out labels to data points needs to be done automatically with a fast labeling algorithm. We introduce Occupancy Bitmap. It's a data structure that helps the labeling algorithm to, first, quickly record the positions of existing marks and labels, and second, quickly detect overlapping of labels to the recorded positions.
Taylor coil flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Data lakes can contain millions of tables. Data portals have tools like keyword search to find data sets, but often researchers don't care about semantics, but rather structural metadata. Can I find a data set with many rows, few columns, and preferably a high number of unique values? Log Prospector visualizes structural properties based on the user's needs and helps researchers fish out data sets with appropriate structural properties.
In this presentation, we introduce a provenance library, Track, which makes implementing provenance in web-based tools easy. Track introduces a novel storage model for web-based provenance tracking and has an associated history visualization, which can be fully customized. Track also contains multiple ways to save and share individual states or entire sessions of an application and ensures that exported data is easy to analyze in interesting and unique ways.
General audience is likely to become distracted during the ever-changing animated visualization and reluctant to consume the entire animation. Informed by the role of foreshadowing that builds the expectation in film and literature, we formulate and apply visual foreshadowing on animated bar chart to improve its engagement. In addition, we implement a proof-of-concept authoring tool and conduct a user study to learn the efficacy of engagement enhancement of our approach.
DVR has always been from considerable interest to the scientific community. To this day, traditional desktop setups are the gold standard. However, what if we could utilize DVR in virtual reality? Now you think, VR and DVR are so computationally expensive, how is this even feasible? Come to my talk and we present you a straightforward solution to visualize volumetric datasets with high refresh rates on VR devices.
All right. Hi, everybody. Welcome to the opening session for IEEE VIS. This is the VAS 2020 group. I'm Ross Majeski.
I'm Sylvie Miksch. Hello.
I'm Brian Fisher.
I'm Jian. Hi. A very big thanks to our organizational committee, our paper chairs, short paper chairs, poster chairs, and all the co-chairs for the other events. We also would like to thank our steering committee and our program committee. A very special thanks to our program committee members, because our program committee members had a very heavy duty this year. Most committee members reviewed 8 papers and some even reviewed 9 papers. So some of the assignment happened during the middle of the reviewing process due to the changes caused by COVID-19, the difficult situations. They did lots of hard work in not only reflected in review, but also in the in-depth discussions, as well as in the sharpening process. We also like to thank all our external reviewers for their hard work.
And we'd like to thank all of the other people that make VAS 2020 possible, from TVCG to our Best Paper Committee to all of the VIS 2020 organizations. So a big thanks for all of their awesome job. And now, of course, people always want to know about the VAST review process. Well, this year we had 210 initial submissions, up from 170 in 2019. Each paper is assigned to 2 PC members and 2 external reviewers. During the first review cycle, 52 papers were conditionally accepted to the TVCG track. 10 papers were conditionally accepted to the VAS conference only track. After the second round review, we had 51 papers that were finally accepted to VAS 2020 through TVCG, and 10 in the conference only track, giving us an overall acceptance rate to VAS of about 30%. And we can take a look at the different paper statistics and trends. So the score distributions and acceptance, here we see the histogram. The blue bars in the histogram show the count of papers that were rejected and their score range. The red papers, the red bars are those that were accepted to TVCG, and the green are those for the conference track. We can also look at where our papers are coming from. We see the 3 largest country contributors by first author's primary affiliation is the United States, China, and Germany. And we can also look at acceptance rates by paper types. We have papers in theory, systems, evaluations, applications, and algorithms. And this takes us to our Best Paper Awards.
And we are gratefully thanking Remco Cenk, who was chairing the Best Paper Award Committee, and Min Chen and Liz Mirai. And the basic process was that we as paper co-chairs selected the 6 best ranked papers according to the content. And then the Best Paper Committee compared the different visions and the different directions, and independently selected 1 best paper and 2 honorable mentions. And we are really proud to present the Best Paper 2020, and the Best Paper 2020 is Wetlit, a visual analytic system to assess, understand, and improve traffic light detection. Congratulations. And as mentioned, we had 2 honorable mentions, and the first honorable mention is In Search of Patient Zero, visual analytics of pathogens transmission pathways in hospitals. Thank you. Congratulations. And the final paper?
Another honorable mention goes to Preserving Minority Structures in Graph Sampling. Congratulations.
And with that, that takes us to the paper talks. So we're looking forward to an exciting VAS 2020. Thanks, everyone.
Thanks and enjoy.
Thanks.
Bye-bye.
Enjoy.
Bye.
Welcome to InfoVis 2020. We are so happy you're here with us today. And I'm excited to launch the InfoVis 2020-26 annual InfoVis meeting and our very first virtual one. So wherever and whenever you are in the world, we're happy to see all this crazy, amazing research together. So I want to give you a small flavor of the trend and growth in research this year. We see really a lot of growth in what we could call recommender system, building from years of research in machine learning and AI, but also from all of the body of work on visualization design and to establish good practices. We also see a growth in Bayesian approaches for evaluation, reflecting the use of InfoVis to help people construct knowledge. Finally, storytelling and communication are still big in our community, and we see more depth and understanding of what we could call visual immersion system. So I hope this gets you excited to stay and hear about all of the different exciting research we have, and you get inspired by this program.
Now a few words about our review process. 10 days before the deadline on March 21st, authors submit their abstracts and metadata for each submission, at which point the program committee are able to declare conflicts and also bid on papers they want to review. On the deadline, March 31st, authors then submit their full papers and materials, at which point the program chairs, in other words, I and my colleagues here, have an opportunity to look at papers and identify ones that are out of scope or incomplete. The remaining papers go to our program committee, who then assign 2 external reviewers. So for each paper, there's 2 external reviewers and 2 program committee members for a total of 4 reviews. Based on these reviews, the program chairs, us, make a decision which papers to accept and reject. The papers that are conditionally accepted go back to review to authors who have a chance to make revisions, which in turn are reviewed by the reviewing panel for each paper. And that's another opportunity for papers who don't quite meet the bar to be rejected. After that, the authors are fully accepted, and they have an opportunity to make their paper camera ready. And those are the papers that you actually will see this week in the conference.
So what was submitted for review this year? We received 251 papers following an extended COVID-related deadline. Nearly 1,000 reviews from almost 400 reviewers led to 64 of them that you will see this week being accepted. The majority of the 361 external reviewers each reviewed a single paper each, although some reviewed more. Among the program committee reviewers, the majority reviewed about 7 papers each. We're grateful for all of your efforts in reviewing in a difficult year. The acceptance rate of 25% has remained stable over the last decade or so, although the number of papers submitted to InfoVis continues to grow to a record 64 this year. The scores given to each paper by the 4 reviewers influences the decision to accept or reject, but doesn't wholly determine it. Discussion amongst reviewers and fit within the conference also plays a role. The balance between paper types remains similar to recent years. We don't see a strong association between paper type and score, although application design study papers have tended to attract lower scores.
The way that we selected the best paper and honorable mentions for InfoVis this year started with us considering all of our top ranked papers that we had. And from these, we ended up selecting 8 really excellent papers that we felt span the diversity of paper types and topics that we had in our pool of submissions for this year. These 8 papers we sent to our best paper committee, who did an independent review. And that committee consisted of Stephen North, Aidan Slingsby, and Anders Jennerman. And we want to give a huge thank you to these 3 excellent researchers for their time and efforts in considering these papers. So this committee came back, and from this pool of 8 papers, they selected 4 honorable mentions and 1 best paper. Our first honorable mention is data visualization, enabling deeper understanding of data using virtual reality. The second honorable mention is a design space of vision science methods for visualization research. Third, we had a generic framework and library for exploration of small multiples through interactive piling. And fourth is a simple pipeline for coherent grid maps. And then for the best paper for InfoVis this year, we have visual reasoning strategies and satisficing, how uncertainty visualization design impacts effect size judgments and decisions. So a huge congratulations to all the authors involved with this really excellent work. We feel that these awards truly give a wonderful overview of some of the most exciting research that we see going on this year at InfoVis. Thank you, and we hope you enjoy the conference.
Good afternoon, and welcome to the IEEE SciVis 2020 Papers Program. I'm Peter Lindstrom, one of the 4 paper chairs for SciVis 2020. Now, it's been a challenging year for many of us, and I'd like to start by acknowledging all the people behind SciVis 2020 that have made this conference a possibility. That includes my fellow paper chairs, as well as the chairs for short papers, panels, tutorials, workshops, and many of the other events here at IEEE VIS. Thanks also to the SciVis Steering Committee, as well as the 69 members of the SciVis Program Committee that handled almost 500 reviews this year, and also wrote summary reviews for our many submissions. None of this would have been possible, of course, without all the volunteers that reviewed papers for us. So a big thanks to them. They did an excellent job getting all their reviews in on time despite all these challenges. I'd like to continue with some statistics on the submissions this year to SciVis. We received 159 abstract submissions, out of which 125 of those were turned into full paper submissions. We were able to accept 32 of those for an acceptance rate of roughly 25%. And this year's SciVis paper program is also complemented by 13 papers from TVCG that have been published over the past year. What this chart shows here is the historical number of submissions as well as accepted papers over the past few years. And what we're seeing is essentially that the number of submissions holds fairly steady. We saw a small dip last year, but we had a strong comeback this year. We're also seeing that the number of accepted papers is fairly constant, around 30 or so. This chart here shows a breakdown of paper categories as categorized by the authors themselves into theory, evaluation, system, application, or algorithm. And as is consistent with previous years, we're seeing that the algorithm category remains the most popular one, followed by application papers and system papers, with only a handful of submissions in the evaluation and theory categories. This histogram shows the average reviewer score, with 1 being the lowest and 5 being the most favorable one. We can see that out of the 32 accepted papers, all of them received average scores of 3.0 and above, while the average reviewer score across all papers is around 2.7 or so. This chart shows a breakdown of country in terms of the primary author's home affiliation. And what we're seeing is that the US, Germany, and China remain the dominant countries of origin of these papers. But we're also seeing a healthy diversity and with many papers represented this year. I'd like to move on to the SciVis 2020 Best Paper Award. We invited a Best Paper Award Committee that consisted of Claudio Silva, Torsten Muller, and Deborah Silver. And the paper chairs nominated 4 papers to the committee, out of which the committee chose 1 best paper as well as 1 honorable mention. And this year's SciVis Best Paper goes to the paper Objective Observer Relative Flow Visualization in Curved Spaces for Unsteady 2D Geophysical Flows. And I hope you had a chance to sit in and listen to this paper presentation earlier this morning. An honorable mention goes to the paper Interactive Black Hole Visualization, which will be presented in the Planets in Space session Thursday morning at 8 a.m. I hope you get a chance to attend this presentation. And we'd like to give a big congratulations to both of these papers. Now, I'd like to conclude with some acknowledgments. First of all, we'd like to acknowledge the authors and reviewers for all their hard work in submitting and reviewing papers for this program. In particular, we appreciate the authors' patience and diligence in getting their camera-ready papers turned in and their presentations done on a very compressed time schedule this year. We'd like to acknowledge the various committees, as well as the liaisons between SciVis and these committees. A big thanks to Klaus Muller, the TVCG editor-in-chief, for his flexibility in allowing us to push the deadlines back about a month this year. Also new this year was that camera-ready papers were submitted through the IEEE submission portal instead of PCS as been done in previous years. So we would like to acknowledge Patrick Hellenberger at IEEE for all his help in organizing and handling all of these submissions, as well as James Stewart, of course, at PCS for his continued support. And finally, we'd like to acknowledge all the student volunteers who helped us organize all the information on about 200 papers that are being presented this year at VIS that really helped us with session planning. And I hope you all enjoy the SciVis program this year and all the other events at VIS. Thank you.
Druid.js is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Druid.js is a web tool using DR. You just need to import Druid.js, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the Xinke model is not easy to understand. We introduced an explainer and interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the explainer, users can progressively explore the Xinke model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
In this study, we designed a system named Quadratic Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained datapath extraction method, a river-based visualization, and a contribution analysis method.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
Tableau helps you see the stories in your data.
It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
The recent COVID epidemic has triggered several different crises that are testing our civilization's potential for both coordination and cooperation. Data about infection rates and their growth has been the main source for public discussion and has inspired many visualization works. We propose a VA approach that incorporates a growth predictive model. This allows the correlation monitoring of the virus population development. We also can relate it to different government response events, as well as identify key dates.
In a visualization, laying out labels to data points needs to be done automatically with a fast labeling algorithm. We introduce Occupancy Bitmap. It's a data structure that helps the labeling algorithm to, first, quickly record the positions of existing marks and labels, and second, quickly detect overlapping of labels to the recorded positions.
Okay, welcome everybody to these full paper sessions on creating and sharing the visualizations. We have 6 great presentations that will show us some breakthrough in different aspects of both creating and designing new novel visualization and also in sharing data sets. To move on and leave more time for question and discussions, I would like to start straight away with the first presentation, which is PlotThread, creating expressive storyline visualization using reinforcement learning, and it will be presented by Tan Tang.
Hi everyone, my name is Tan. Today I wanted to introduce my recent work, PlotThread, creating expressive storyline visualizations using reinforcement learning. This is a joint project. I would like to thank all co-authors for their outstanding work. Storyline visualization is an effective method to present the temporal relationships among entities, which are widely used in different fields, such as presenting movie narratives and recording meeting minutes. To optimize storyline layouts, researchers propose 3 aesthetic goals. They are minimizing line crossings, minimizing line vigors, and minimizing white space. In the past few years, researchers have developed various approaches to generate storyline visualizations. Although these methods target at different research problems, they can be mainly divided into 2 groups. The first groups are the optimization methods, while the main goal is to pursue more aesthetic layouts. The second group are the interactive methods, while the main goal is to produce expressive layouts, which may lose some aesthetic quality. To bridge the gap between 2 sides, we developed PlotThread, a novel authoring tool for storyline visualizations. PlotThread is a mixed initiative design tool, which integrates an AI agent to support the collaborative design of storylines. PlotThread also provides users a set of easy-to-use interactions. For example, users can change the order of characters using sort. Attract and repel can change the distance between line groups. Transform can change the overall trend of layouts. Drag can relocate line groups. Stylish can embellish individual lines, such as changing their colors or line styles. In PlotThread, users' task is to initiate a storyline layout, while the agent will generate alternative designs, so that users can select what they want. However, developing such an agent is not an easy task. Here comes 2 major challenges. First, we don't know what kind of model architecture can be used to train the storyline agent. Second, we don't have sufficient high-quality storylines for the learning problem. To solve the first challenge, we propose a novel reinforcement learning framework. To solve the second challenge, we use iStoryline tool to generate a benchmark dataset. Now we introduce the basic ideas of reinforcement learning. First, we have an agent, and the environment, which is the storyline visualization in this work. Just like human, the agent has some actions that can change the environment. The agent can also observe the environment and get some feedbacks, which are called rewards. The training goal of the agent is to maximize the cumulative rewards. Next, we introduce how to define the actions. There are 2 ways to define the actions. The first is we can use the freeform drawing tools. However, these tools do not invoke any optimization model, which may produce low-quality storylines. To produce aesthetic storylines, we determined to use the high-level interactions inherited from iStoryline tool. We employ 3 high-level interactions, namely shifting, bending, and scanning. As we can see from the demos, these interactions can change local regions, but still preserve the aesthetic quality of our raw layouts, because they are translated into constraints, which can be integrated into the optimization model to control the generation of storylines. After defining the actions, we now introduce the rewards. In our work, we require the agent to produce a list of alternative designs based on the targets. To resemble the targets, the agent must capture the main trend of storylines. Based on this requirement, we define the reward as the similarity between the alternative and the target layouts. Specifically, we calculate the rewards from 3 aspects. For each aesthetic goal, we define 1 similarity measure, and the total reward is the linear combination of the 3 measures. After defining actions and rewards, we next introduce the agent. The agent is comprised of an actor which predicts actions, and a critic which gives action values according to the environment. We first define the actor-critic network using convolutional neural networks, because they are effective in dealing with visual information. However, in our experiments, we found such complicated networks are easily overfitting. Thus, we remove the convolutional layers to simplify the network structure. Moreover, our action space is a mixed-type space, which cannot be easily solved by typical actor-critic algorithm. Thus, we use 3 networks to deal with different actions. Finally, we employ a greedy modular to select the optimal reward and action. To produce sufficient training data, we generate storylines using iStoryline tool. In our last work, we collected 74 hand-drawing storylines. We first extract the story scripts from them manually. We then input the story scripts to iStoryline. For each story, we use different interactions and model parameters to generate different layouts. In total, our training dataset has more than 20,000 storylines. Once we have sufficient training data, we begin to train our agent. The agent should modify origin layouts to resemble the target layouts. By comparing the 2 layouts, the agent first obtains a reward, and the critic will give a value to the agent, so that the actor can predict the next action. With this action, the agent can use iStoryline to generate the next layout. The agent continues to compare the obtained layout with the target layout. He then obtains a new reward, predicts a new action, and finally obtains the new layout. This training process will continue until a final layout is obtained. After training the agent, we use it to resemble the target storyline, which follows a stair-like trend. The showing demo indicates that the agent can successfully capture the main feature of the target. With the storyline agent, we now introduce how to design storylines in a collaborative way. We first specify the initial layout using diverse interactions, such as drag and transform. We then invoke the storyline agent to provide alternative layouts. We can smoothly navigate different designs and choose what we want. After that, we can further embellish the storyline to make it more expressive. To evaluate our model, we conducted a qualitative experiment. The first row are the originals. We changed their shape using the PlotThread interactions to simulate the real authoring process. We then used the second row as the target storylines. The layout trends are identified manually. The last three rows are the model results. The agent can successfully capture the main trend, while still preserving a good aesthetic quality. We also compare our model with a baseline method. The baseline method randomly searches the action space and predicts the next action using a greedy schema. The left chart indicates that our model may lost at the beginning, but it finally achieves a better layout than the baseline. The right chart indicates that, in some special cases, our model may spend more time to find the optimal, but the total time is still acceptable during the authoring process. Let's conclude this work. We developed a novel reinforcement learning model to support the co-design of storyline visualizations. We implemented PlotThread, a mixed-initiative authoring tool which seamlessly integrates AI agents to design storylines. In the future, we plan to integrate more design tools to support users' design requirements. We also plan to employ parallel computing to accelerate our agent. Finally, we are very interested in supporting the design of storylines without any story scripts. We would like to thank all sponsors who helped with this joint project. Thanks for your listening. I'm happy to take any questions.
Let's thank our speaker. Thank you very much, Tan, for the nice presentation. And we already have a couple of questions. The first one is, if the views are synchronized, will the interaction from one person surprise or interrupt the other person?
Okay, thank you. I guess the question is like will the person, the user interact with the agent, because in our authoring tools, they are not a collaborative tool for different papers that actually work with the AI agent. So the question, the answer is actually no, because the agent only produces the final result, so the users can choose one from the final result, and the result, if you don't like it, you can choose another one, and these results are basically they are more similar to the targeted storyline that the agent are creating, so they won't surprise the users.
The second question is probably more straightforward, and they are asking, is the storyline training dataset publicly available?
Yes. We actually have two types of dataset. One is the hand-drawing storyline visualizations. We actually released it on my last work at Storyline, so you can actually check it through search using the searching bar in GitHub. And we also release our algorithm code, so you can use this code to using the hand-drawing storylines to generate a more diverse training data set.
Perfect. And we have one last question, and we're perfectly on time. So the last question is this approach extended to other application domain for which we have aesthetic measure, for example?
Okay. I think the idea of reinforcement learning actually can be extended to many different fields, and it depends on how you define the actions and the rewards. In our case, we using the 3 aesthetic goals. I don't know how much goals you have, but yes, I think you can do that. Depends on your mathematical formulations.
Perfect. So we have to move on with the next talk, with the next presentation. There are probably a few more questions popping up in the Discord channel, and so we invite the audience and the speakers to keep the conversation live. Now we move on with our next presentation, which is Lyra 2, Designing Interactive Visualizations by Demonstration, and the presentation will be led by Jonathan Zong.
Hi, my name is Jonathan Zong, and I'm excited to share our work today on Lyra 2, which is a system for designing interactive visualizations by demonstration. This work is an extension of Lyra, which is a prior visualization design environment that allows people to create visualizations using direct manipulation and drag and drop interactions. However, Lyra's output was restricted to static visualizations. Other similar tools like Tableau and VisDoc support some interactivity, but either hardcode specific interactions or offer only a limited typology. To create custom interactive visualizations, users instead turn to textual specification languages. Vega Lite and Vega are prominent examples in this space, and in fact, Lyra exports visualizations by generating Vega specs. However, using text-based languages to design interactions has several usability drawbacks. The main one being that there's a poor closeness of mapping between text and interaction, which makes the relationship between input and output less clear. With Lyra 2, we're trying to bridge this gap by exploring graphical interfaces that support custom interaction design. And the main design values we prioritize in this process are expressivity, the ability to support a diverse range of custom interaction designs, while also maintaining a close mapping between the designs users have in mind and the way they express those designs. So here's a screenshot of the Lyra 2 interface. The main component is the visualization canvas, where the user can create and edit graphical marks through direct manipulation. The visualization canvas always reflects the state of the final output visualization. At the top, we have a panel for data tables, which show any datasets that have been imported. Users can drag the fields from the table onto the visualization canvas to bind them to properties on marks. They can also create and edit data transforms here. On the right side, we have the toolbar. This is the main way to add new graphical marks and also to add new interaction designs, as we'll discuss in a moment. Users can also export their visualizations as JSON files in the Vega format. And finally, on the left, we have the Property Inspector sidebar. Here, users can dive into the details of different parts of the visualization, including interactions, to customize their properties. So how do you create an interaction in Lyra 2? First, the user initializes a new interaction by adding it with the toolbar. Then they use their mouse to demonstrate an interaction directly on the visualization canvas. The system interprets this demonstration using a set of heuristics and suggests possible interaction designs. Finally, the user can view live preview thumbnails that show what the visualization would look like with that interaction applied. They can also further refine their demonstration or configure the interaction in the sidebar. Let's walk through an example of that workflow. This Seattle weather exploration visualization is featured in Vega Lite and Vega's example gallery. It involves two views. The scatter plot has a brush interaction that reaggregates the histogram, and selecting a bar on the histogram filters the scatter plot. To recreate this visualization in Lyra 2, first we demonstrate a brush on the top view by dragging on the scatter plot. Because we dragged horizontally, the system automatically constrains the brush to the x-axis. We then go to the inspector on the left and click to apply the brush selection to the scatter plot's color and opacity. We also apply it to drive a filter on the bottom view. And you can see that the encodings and filter are immediately active on the canvas. Next, we demonstrate a new click interaction on the histogram. We want to use the selected bar to highlight all matching points in the top chart. So we choose to project our selection in the inspector. the system automatically selects the field for us to project on based on heuristics. We then choose to apply the selection to the color encoding on the histogram and to a filter on the top view. And again, the filter is immediately live on the visualization canvas. Here's the final multi-view filtering interaction, which can be tested live in the visualization canvas. We added it to the static visualization in just a few clicks. So how does Lyra 2 internally represent interactions? Interactions consist of two parts, selection and application. Selections determine how input events select data records. Point selections select sets of discrete data records, while interval selections define a continuous range of records. Applications determine how selections drive behaviors on other elements, including visual encodings on marks, so color and opacity, on scales, such as for panning and zooming, and also transforms, like filtering. Lyra 2 also unwraps selections into signals, which are dynamic variables that enable even further custom behavior. Here's another quick example. So what if we want to create interactions that aren't selection-based? In this line chart example, we want to have a vertical rule that follows our mouse and brings up tooltips on the data points for that year. Mouse coordinates are continuous, so may not exactly map onto a date record in the dataset. Lyra 2 exposes mouse position as a signal in the bottom of the inspector, which can be dragged and dropped onto properties, like X position, just like data fields could be drag and dropped. Lyra 2's model diverges from Vega and Vega Lite in a few important ways. Our abstractions are designed specifically to meet the needs of a graphical interface. For instance, Vega Lite has three types of selections, point, multi, and interval. Point and multi are both discrete selections, so from a UI standpoint, they're both demonstrated by clicking. Therefore, Lyra 2 treats them as one concept. We also notably treat applications as a first-class primitive. There's no corresponding concept in Vega or Vega Lite. In Vega Lite, applying selections to marks, scales, and transforms all have subtly different syntax, which are irrelevant to a graphical interface. Abstracting over these distinctions not only simplifies the mental model for users, but also allows us to associate interactions with both the source selection and the target element, and surface this as a two-way linking in the interface. In Vega Lite, you would have to do a text search for this information, but our design increases user visibility into the system state. Lyra 2 maps user inputs to interaction suggestions using heuristics, which are implemented as a series of if-else production rules informed by design principles and exploratory tests. In the first step, the system looks at the user input type. It maps clicks to point selections and drags to interval selections. It also fills in default configurations based on the visualization. In our weather example, the system saw that the weather field was mapped to color in the histogram. Therefore, projecting over it was likely to be meaningful. For interval selections, the system similarly suggests brushes based on the chart type. For example, if a histogram has a discrete X scale and a continuous Y scale over an aggregate field, the system doesn't suggest brushing along the aggregate measure because it doesn't capture a valid set of backing data. In step 2, the system enumerates possible application types based on the marks and scales that are present. For multi-view visualizations, it will also suggest applications such as linking and cross-filtering. Based on the demonstration, the system also enumerates signals in both spatial and data coordinates for use in custom interactions. Point signals also reference the fields of selected points as well as mouse coordinates for hover interactions. And finally, the system infers default choices from the available suggestions in phase 1 and 2 using the demonstration's input event history. For example, on horizontal or vertical drags, the system automatically chooses an x-axis or y-axis brush, respectively. Similarly, when clicking on multiple points in quick succession, the system will default to a multi-point selection. We evaluated Lyra 2's expressive extent by creating a gallery of diverse examples. We analyzed the examples using Yi et al.'s taxonomy of interaction techniques, demonstrating our support for 6 out of the 7 categories in the taxonomy. Lyra 2 does not yet support encode interactions, which manipulate the view directly, for example, by altering mark types or data field mappings, etc. We also evaluated Lyra 2's usability with a user study. We recruited 6 representative users with a range of prior visualization experience and had them recreate 3 examples of increasing difficulty. One user said, "I didn't really know the word brushing, but it was easier to just do it than to say what it is." So demonstration shortened the articulatory distance for expressing interactions. Another participant said, "Being able to test immediately was very useful. Even when it went wrong, I could immediately tell that it was wrong." For them, the rapid feedback loop was useful for prototyping. One participant very concisely articulated a similar limitation that we discovered with the example gallery. What if I want to make interactions that aren't in the suggestions? And this question leads well into our thinking about future work. For instance, how might we go beyond heuristics to adopt recommendation methods such as ranked enumeration? The challenge here is the need for empirically validated principles for evaluating the effectiveness of interaction design. Mixed initiative systems also highlight the need to balance between automation and agency, as we found in user studies where users were frustrated when defaults were applied too aggressively. And finally, like our study participant pointed out, interfaces necessarily impose constraints on what can be expressed within them. Sometimes these constraints are technical, but they can also be informed by principles and conventions, like with our heuristics. Future work should continue to keep in mind the epistemic and ethical implications of encoding design conventions into tools. We're really excited to share this work with you, and you can find more information, including our open source software, on the MIT Visualization Group website. Thank you.
Thank you, Jonathan. Very interesting work. We already have a few questions popping up. The first one is a long question and also an enthusiastic question. So they're asking, how does the system work when considering undoing selections interactions? For example, with the filtering based on clicking the bar chart example, presumably, normally you can just use the undo button, but you have the undo button that you have. But what if there has been further data manipulation and filtering, like changing the brush range in between? So is it clear how to undo specific interactions?
All right. Thank you, everyone, for coming to the session. Thank you, Rita, for moderating. And this is a great question, Thomas. I think it's important to kind of clearly differentiate between interactions in the visualization space versus interactions in the interface space, or like the editor designing space. So what you're referring to, the situation where you click something and then you kind of change the filter state inside of the visualization. These changes are unaffected by the undo redo in the editor, which is about like changes you've made to the definitions of your visualization, if that makes sense. So these would kind of be independent things.
Perfect. So we have a second question. How does the Lyra 2 interface deal with potential conflicts between encodings and application of selections? For example, one may encode a variable with color and also apply selection to color 2.
Yeah, that's a great question, Ham. So in our data structure for applications, when you apply a selection to a mark property, there's 2 fields in the data structure, one for the selected value and one for the unselected value. So in a situation where you've like already mapped a field to the color and then you apply selection to color, your field binding would be preserved as either the unselected or the selected value. So if you don't interact, it'll kind of by default treat everything as selected, right? And then you'll have your kind of original color binding, but then you can set your own unselected value or set that unselected value to a different field, for example.
Okay, unfortunately, we have to move on to our next talk, but there are a few more questions on the channel, and as suggested before, it would be great if you can continue the dialogue on the channel. Our next presentation, it will be Structure Graphics, Flexible Visualization Design through Data-Agnostic and Reusable Graphical Structures, and the presentation will be led by Theophanis Tsandilas.
Hello everyone, I'm Theophanis Tsandilas from INRIAN, the Université Paris-Saclay in Paris. So in this talk I will present Struct Graphics, which is a new approach for designing data visualizations. Now, previous work in the community of information visualization has observed that traditional visualization tools target mainly scientists and data analysis tasks, and in such tools users start with a concrete dataset and produce a graph by mapping the dimensions of the data to the graphical parameters of a chosen template. So in visualization grammars and toolkits can support a richer range of visualizations. But again, in order to create a graph, we describe how the variables of a dataset are mapped to the properties of the visual objects. Now, in Struct Graphics, we follow the opposite direction. So visualization creation is fully driven by the graphics. Data variables are derived at the very end of the process from the structure of the graphics. So the goal of this approach is to support design rather than data analysis tasks. So I will start with an example where I reproduce a flow diagram, a Xinke diagram, which depicts the change in council control after the 2018 local election in the UK. So let's see this example. So I start by drawing a rectangle, and from this I create a stacked bar chart, which you see here after grouping them together. I will then replicate it again, and after repositioning, I will merge the two groups into a larger collection. I now turn to the inspector, and I decide to vary the fill color within each subgroup. You can see that colors are synchronized between the two. As I change the colors, things are consistent between the two subgroups, and then I will continue by drawing the links of my flow diagram. As you see, as I draw the links, the bar heights are automatically adapted. Now, what is more important is that the structure of links is automatically created and is available in the inspector. As I go to the inspector, this is my link structure. I will bring it by dragging to the spreadsheet, and this is a template for my dataset. Then I create a symbolic mapping and then type the values that represent the UK political parties. As you see, other cells of my table automatically change as I type, and this helps encode my data faster. I will then map the flow weights to the number of cancels by using a simple transformation function, mapping, right? And then type my values. And of course, all these views, all the different views of my user interface are synchronized, so I can see how these changes affect my visuals, my graphics. I go back to the graphics to improve the layout. I will also change the gaps, as you see here, between the bars. There is this tool, and also customize the colors. Then I go to the spreadsheet where I choose to display the political parties as labels in my diagram. There is other missing information as labels, so I will go back to the inspector to bring some structure for some properties from the inspector and assign them to data variables. I will turn them to data variables and then show them in my diagram, and this is the final visualization. There is also this component here, which you see here, this is my library, a library that lets me reuse my previous designs. For example, I bring my previous design that I just created the canvas, and I further change it, and I can also bring new data to it. That's it, new data. This is another example, another template, which I used to create a nested area chart. Now, previous work has looked at how designers design for data, and here I summarize some key findings of a study that has greatly influenced my work. A first observation made by the authors of the study is that designers create visualization in a top-down graphical process. A second observation is that they tend to think of how to influence existing graphics that they have already created in the past. Third, designers prefer flexible environments that do not reinforce a specific order of operations. And finally, manual encoding is not only tolerated, but even embraced by designers. Now, in the last few years, the InfoVis community has introduced a range of design-oriented systems, and some of these systems partly require programming workflows, as the ones that you see here. Others focus on the design of expressive data-driven infographics, and the third category supports the authoring of custom visualizations with complex layouts. And I would like to highlight these three systems here for three main reasons. First, because they support similar visualizations as Start Graphics. They also offer vector graphics editing tools as Start Graphics, but what's more important is that their authors gathered together and reflected on their system's limitations and assumptions. And these are two important conclusions about their assumptions. First, that data are appropriately pre-formatted before the task. And second, that people want to author a chart, not design one. So in particular, they assume that users come with a specific chart design in mind. And as a result, graphics are bound to data at the very first steps of the authoring process in these systems. So let's go back to the Star Graphics user interface. So we identify four main components here. So we have a library that enables designers to reuse their past designs. There is a sketcher, which is a vector graphics editor for drawing graphics in separation from any data. The inspector that exposes and structures the properties of a visualization and the visualization objects. And a spreadsheet for turning graphical structures to data schemas, and then exploring some bindings between data and the graphics. Now, Start Graphics visualizations are hierarchies, and as in other systems like, for example, Data Illustrator, they contain marks, such as squares, lines, and text, groups of such primitives, and then collections. So in this example, for example, I highlight a group, the sailboat, within a collection that represents a custom area chart. Groups and collections have similar representation creative process in Star Graphics, but they are, however, somehow distinct. Groups consist of a fixed number of objects, which can be either marks or lower level groups. In contrast, collections group a variable number of objects, which can be marks, groups, or sub-collections. Now, a main focus of the Star Graphics approach is on how to organize the properties of groups and collections without referring to data. So let's consider a collection of four rectangular shapes, and let's focus on these particular properties. We observe that the y-coordinate, the rotation of all rectangles, is common or shared, as I write here. And in contrast, the other four properties, for example, the fill color, are variable, they vary. And we'll see later that variable properties provide the templates of data tables. Now, let's see here how the properties of the children nodes of a collection are grouped in the inspector. So the fill color is a shared property, so when we change it, we'll see that all sibling nodes are also changed. And we can make it, however, variable by dragging, and then change the color of individual children. In contrast, the height is variable here, but we decide to make it share, and now all the children heights are bound together. Now, more generally, a visualization hierarchy can support different levels of sharing, for example, no sharing at all, A-level sharing, B-level sharing, A and B level sharing at the same times, where A and B here refer to the level of nesting, and of course this generalizes to deeper visualization hierarchies. In groups, we can share the properties of a subset of grouped objects. So let's create here, in this example, a group from scratch by replicating the first rectangle. And here I will change the top rectangle to a triangle and also change its color and its height. So star graphics offers a by-example specification approach, trying to bind all common properties of children nodes. After grouping, now star graphics binds the height of the 3 rectangles, but also binds the width of all the shapes together. I can break a binding and recreate it from in the inspector. When I change here the color of all the rectangles changes at the same time. Now, star graphics relies on 2 flexible layout mechanisms. Alignment is easily controlled by the sharing of the X and Y properties of the children in a group or collection. It further provides techniques of persistent distribution and stickiness that helps designers to have full control of the visualization layout. Now, star graphics visualizations are data agnostic, but at any moment, designers can link them with data through the spreadsheet. Here I drag the variable properties of the collection and drop them into the spreadsheet and create a table. I decide to map the x-axis to a data dimension year here. This generates some default values, and I display the variable on the visualization and then type the individual year values. And I see how this updates on my canvas at the left, on the visualization on the left. Now, a full star graphics all star graphics visualizations or their individual nodes can be added to the library. Designers can then easily reuse them. As you see, I add it to the library with just a click, and then I bring them by dragging to the canvas. So visualizations are stored as data-agnostic JSON snippets, and this facilitates their reuse and sharing. Now, we provide a gallery with videos and other resources. Several of our visualizations are replications or variations of examples offered by the authors of Data Illustrator and Charticulator. We also collected feedback by professional designers and InfoVis experts, and these are some comments by 2 designers who were especially enthusiastic about the approach. So one says here, it takes me much longer with my usual software. The other one says that this tool allows to create visually, start visually, then to insert real values. Really easier than struggling with their setting panels and tabs of a pre-existing graph in Excel. Participants also reflected on the distinction between graphics-driven versus data-driven visualization design. I cite some representative comments here. For example, participant 7 argues that both directions are true depending on the task, but also mentions that it's always important to have an idea of how the visualization looks even when data are incomplete or not available. And the other participant here highlights that eventually you always have to plug in data to test a visualization design. Now, I will end with some limitations of the current implementation. First, property structures in the inspector complex as visualization hierarchies grow, and we need to improve the user interface to deal with this complexity. Now, furthermore, building a visualization with a large number of data points can be time-consuming because all data points are manually generated in the sketcher, and a solution is to allow users to populate new data points from the tables in the spreadsheet directly. So you have probably noticed that StratGraphics lacks support for non-Cartesian coordinate systems or custom primitive shapes, which are future goals. So, to conclude, I presented StarGraphics, a system for design visualizations through reusable graphical structures. Code and supplementary materials are publicly available for download, and I will be very happy to provide further details or answer your questions. Thank you.
Thank you very much for this great talk. We already have one question. How do layouts that require embedded data or calculation work in StratGraphics?
So yes, this is a nice question, because it's, I will say, one of the limitations of the current approach, so that yes, we can't provide these kinds of layouts. And I suspect that it's not right, that you need to provide some additional tools to extend it, but it's a good question, as currently it's not supported.
Okay, and we can move on to the next question, which is, I'm curious on the choice drag and drop interaction to bring information in Inspector onto empty spreadsheets. Could you make the Inspector to have tables in it?
So yes, so actually what happens is that the inspector has a kind of tabular representation of, but not data, it's properties. Properties are organized as tables. And then what is important, because there is no explicit mentioning referring to data, that's why the spreadsheet is not automatically populated, but it's actually the user who decides which particular columns are of interest or which particular subtables and from which part of the tree hierarchy. So the idea is that there is this flexibility that the designer picks the particular structures or kind of types of or which properties that can be put in the spreadsheet. Actually, you can have different, bring the same properties to different parts of your spreadsheet and even associated them with different data schema. So this is more to have this flexibility that you go from the properties to the spreadsheet.
Fantastic. Then we have one last question, which is are there potential conflicts between the graphical structure and the real data set when you try to link the graphics with the data?
So yes, this is what happens is that when you actually build the graphical, when you bring the property structures to the spreadsheet and become data, so it's actually the bindings of your graphics that make your data force the dependence on the data. So if you have a data set that actually does not follow the correct structure of the graphics, yes, there is can be a conflict. So there is a kind of, if you just copy paste the data are not in the correct format, right? There are maybe some problems. So it's more, the idea, the concept allows more about manual encoding. You bring the data and then you have to discover, of course, we go back to the graphics and you see conflicts. Yes, this can happen if your data are not organized as you want it in your graphics.
Great. We have to move on to our next presentation. Thank you, Theophanis.
Okay, thank you.
A few more questions in the Discord channel. Feel free to keep the conversation going. Our next presentation will be VIS code, embedding information in visualization images using encoder-decoder networks. And the presenter will be Peijing Zhang.
Hello everyone, I'm Peiying Zhang from East China Normal University, and today I will present our paper on VIS code, embedding information in visualization images using encoder-decoder network. This work is supervised by Dr. Chenghui Li. VIS code is a framework for embedding information into visualization images and reconstructing the information. So what can VIS code do? Let's see some typical scenarios. With VIS code, designers can implicitly embed additional information into the visualization image instead of using explicit icons like QR code. First, when designers and programmers collaborate, they require two different types of media: visualization templates from designers and corresponding data files. It is more convenient to transmit just images with VIS code. Second, it is difficult to recognize large data, such as network diagrams or scattered data in information visualizations. While VIS code can be used to encode and decode the original large data in a static image without pattern recognition. Moreover, VIS code can turn a static visualization into a dynamic form. Thus, animations and common interactions can be applied. Later, I will talk more about the details. Now, let's move to the related works. Previous studies have proposed to be directly embed messages into the letters of text using complex perturbation rules. Recent studies have combined deep learning with steganography. These methods have been proposed for natural images and make use of rich and mature features, while the features of data visualizations are quite distinct. Besides, several researchers have applied a pattern recognition approach to visualization images to retarget the color theme, but the effectiveness of data recognition is still related to the form of visualization. Different from the prior works, we focus on encoding a large amount of data into information visualization images while preserving their visual perceptual quality. Our VIS code system has three main components, such as the Visual Importance Network, Encoder Network, and Decoder Network. First, the Visual Importance Network processes the input chart and output a visual importance map. Next, an encoder network embeds secret information in the chart. The encoded image is then sent to the user, and the user can send it to others by digital transmission. When a user wishes to obtain the detailed information hidden in the chart, the encoded image can be uploaded to the decoder network. After data recovery and error correction, the user receives the decoded information. A visual importance map assigns different scores to different regions of an image, which can help to preserve the visual quality of the important content in the encoding stage. Inspired by some state-of-the-art silencer detection models, our architecture is based on a UNet-style encoder-decoder network. Accordingly, to obtain more accurate high-level semantic context information and low-level details, we use a hybrid training loss and we train on the SciVis dataset. Our results are more similar to the ground truth distribution. The encoder network is designed to embed information within a carrier chart image while minimizing perturbations in the encoded image. The decoder network recovers the embedded secret information from an encoded image. First, we construct a dataset of information visualizations and QR codes. We use several popular visualization libraries, such as D3, eTrust, and EntV, to generate carrier visual designs in 10 categories. Here shows the distribution of this visualization dataset. We randomly generate QR codes with various character lengths and various error correction capability levels. Inspired by DeepStack, we use a network structure similar to that of an autoencoder. Different from DeepStack, we introduced the visual importance map to supervise the encoder network. The decoder network is supervised with a cross-entropy loss. During the training process, we train the encoder and decoder network simultaneously. That is, the joint loss incorporates both the visual quality of the coded image and the reconstruction error. The results demonstrate that our VIS code model can embed information while preserving the perceptual quality of the original chart. Embedding a large amount of information in an image is a challenging problem because it is easy to generate obvious noise or cause deviations in color or texture. Hence, we propose a method for the large-scale embedding of information in regions to which the human visual system is insensitive. We first split the text into several blocks. Then we find a set of optimal regions with the smallest values in the visual importance map while avoiding overlap of the region proposal boxes. We use average pooling to calculate a value for each region box. We preserve the top left region box for embedding the position information of the selected regions. In the decoding stage, we utilize the position QR code. Here shows some results. This code can embed information in various types of chart images with better visual quality. Moreover, this code can be used for a number of applications. We implement an interactive system. The input metadata can be hidden in the input visualization image. This code also provides users with a robust source code embedding function. In this scenario, we encode the source code data into a static visualization image. The visualization images and source code were generated using D3 and E charts. When the user inputs an encoded image, the system decodes the source code from the image and dynamically generates and displays the visualization file. This code can be used to encode the original data into a static visualization image in JSON format. For users, the input is an encoded static image, and the output is a visual effect of different styles. We evaluate our VIS code model from several aspects. We compare our method with two state-of-the-art steganographic methods in three metrics: PSNR, SSIM, and LPIPS. Besides, we recruit 30 users to choose the best steganographic results of three methods. This code is rated higher than others. We also evaluate the quality of encoded images with different input text lengths. This code can encode large-scale data while preserving the perceptual quality of the visualizations. When users share encoded chart images through digital transmission, corruption or attack may occur. We analyze for typical scenarios: adding watermark, adjusting brightness, applying rotation, and applying JPEG compression. This code outperforms other two methods. The time performance is relatively stable for encoding different lengths of information to images with the same resolution. The leading cause of different time performance between images with diverse resolutions is the calculation of the visual importance map and the embedding region proposals. In conclusion, our main contributions are deep learning framework with high-quality large-scale information embedding in visualizations. The VIS code has certain limitations in addressing large deformations of the coded images. There is an upper limit on the amount of embedding information. In the future, we plan to extend VIS code in camera capturing and light-aware steganography. We also plan to collaborate with designers and developers to obtain feedback and improve the user experience. Thanks for your listening.
Thank you very much for your very nice talk. And the floor is open to questions. We already have one in the Discord channel. And the question is, have you tested this outside of InfoVis as well? I'd be interested to see how regions of SciVis would be marked as important for data embedding.
Hello?
Hello?
Well, our paper, okay, is how regions. Well, I know, well, good question. First we use and MIT SciVis dataset is a dataset for information visualizations, and so the saliency of human region is more relatively to the information visualizations. We haven't tested how it performed in the SciVis. In future, maybe we can explore the factors to which factors to affect the difference between the InfoVis, information visualization and science visualizations.
Great. It will be a very interesting extension. We have another question which is asking, is there accuracy confidence issue with the decoding? So for example, correctness of the decoded data.
Well, thanks for the question. We do some experiment first in our paper we use text recovery accuracy to assess the performance of our model in the decoding stage. The text recovery accuracy means, for example, of 100 images, 99 were decoded completely correct, but it is hard to achieve 100% accuracy without error for all images. For example, with the same image size and the encoded data bits, the images with more complex texture and rich color content are easier to decode successfully. So it's related to the type of the chart images.
Great, thank you very much. There may be another, another question showing up on the Discord channel, but we need now to move on to our next presentation. So thank you, Beijing. And we move on to our next presentation, which is Charten, Reviving Chart Images with Data Embedding. And the presentation will be led by Bin Zhu.
Our paper is titled as Charten, Reviving Chart Images with Data Embedding. My name is Bin Zhu. I represent the authors from Huazhong University of Science and Technology and Microsoft Research Asia to present this paper. Charts has been widely used in our daily life. Charts can be easily created with an authoring tool. A chart object is first created from data and then published as a bitmap image to be used in a document, website, etc. The information conveyed in a chart image can be easily comprehended by humans, but hard for machines or visually impaired users to understand. As a result, a lot of information has been locked in chart images that is hard to be reused. To address this issue, many methods have been proposed. They are all based on image recognition to identify the type of a chart, recognize text, and detect objects in the chart to recover the chart type, data, and attributes. They have made a significant progress, but still have several limitations. They typically work well only for simple chart types, such as bar charts, pie charts, and line charts. The recovered result may be incomplete and inaccurate that the original chart cannot be reconstructed. In this paper, we present a novel method called Charten that uses a completely different approach. We embed chart data and attributes or generic data into a chart image. The embedded data becomes an intrinsic part of the chart and is preserved after image format conversion, copy and paste, etc. There are three major requirements in our approach. First, perceptual quality. A data embedding chart image should not interfere with the normal usage of the chart. Second, robustness. The embedded data should be extractable after common operations on the chart image. Third, capacity. All the necessary data should be embedded into a chart image. These three requirements are inversely related to each other. It is generally more robust when the perceptual quality is lowered or capacity is reduced. We typically need to strike a balance among these three conflicting requirements. To ensure perceptual quality, we embed data into the background of a chart and the foreground is untouched. This is because the foreground is informational and the focus of attention. To increase robustness, we pack the data in small segments to prevent error propagation and apply error correction and detection to ensure that the tracked data is correct and complete. This is flowchart of Chatham. For input chart image, Chatham detects its background and embeds coarse and fine marks into the background. 3 or 4 coarse marks are placed at the corners of a bounding box of embedding regions, and at least 3 fine marks are placed on a grid. Input data is packaged into segments, and segments are partitioned into block sequences. Each block sequence consists of one or more data blocks, plus a start block and end block to identify the block sequence. A block contains a fixed number of logical bits. Each logical bit is mapped into a block of pixels. We used 2 by 2 pixels as a block in our experiments. Pixel values in a block are adjusted to above or below the local average to carry a logical bit of 1 or 0. Each block sequence is embedded into a continuous background region not taken by coarse or fine marks. The embedding pattern is weighted by a preset weight. To adjust the perceptibility of the pattern, a higher weight means that the pattern is more visible. The result is data embedded chart image. This is a flowchart of data extraction. To extract data from a chart image, first, Chatham detects the background of the chart, detects coarse and fine marks to estimate rough and accurate transformation parameters that the received image may undergo, and registers the received image to the ranged shape and size of the chart. Then it detects each block sequence to extract the raw data, identifies each segment, conducts error correction, and validates the extracted data before output. This shows the ranged chart and 8 embedded charts with different weights. We can see that the higher the weight is, the more visible the embedding pattern is. To evaluate Chatham, we collected typical charts from the internet. We used 4 chart types, and each type contained 3 charts in our experiments. These 12 charts are shown here. In our user study, each participant first saw an arranged chart and then rated embedded charts with different weights shown at random order. 5-point Likert scale ranging from high impact to no impact at all was used for rating. This figure shows the resulting mean of ratings. We can see that weight at 17 or below receives a rating above 3.5, which means these weights are well acceptable. The largest 2 weights are around 2.0 or below, which means they are unacceptable. The other 3 weights are between them. As a result, we choose weight 17 as the default weight for Chatham to balance perceptual quality and robustness. We evaluated Chatham's robustness at default weight. The results are shown here. The left table shows the results when a chart is randomly scaled up and then screenshot, as well as rotations at positive and negative 30 degrees. We can see that their precision and recall are very high. most above 99%. The right table shows the precision and the recall of the JPEG compression at a quality factor of 80, 70, and 60. We can see that their precision is above 95%, while the recall reduces to about 80% when the quality factor decreases to 60. For uniform brightening and darkening, we get 100% for both precision and recall. For gradual brightening and darkening, the resulting precision and recall are both near 100%. The capacity of a chart image depends on the size of the chart and also the size and shape of its background regions. This table shows the raw capacity, which is the total number of bits embedded into a chart, including head bits and parity bits. The raw capacity ranges from 10K bits to about 75K bits for charts of size from about 480 by 480 pixels to about 1000 by 600 pixels. It also shows the capacity of user input after compression that survives two operations. The first is random scaling up and then screenshot. The second is JPEG compression with the default quality. The input capacity ranges from about 650 bytes to more than 3800 bytes. We also measured runtime for both embedding and interaction on laptop. The left table shows the embedding runtime and right table shows the interaction runtime, including each major module and their role. We can see that the overall runtime ranges from 0.3 to 0.8 seconds for embedding and 1 to 2.7 seconds for interaction. We're going to show 3 demos.
The first demo is the Excel add-in to create charts with embedded information. This is an Excel chart object created from the sales data table. You can select it and click the Chart M button to embedded information into it. In the side panel, you can specify information to be embedded. You can include underlying data table and add additional description for the chart. Click the Embed button. The embedded chart image is generated. You can further save it as a file and use it in the future. The second demo is the PowerPoint add-in to leverage the embedded information to redesign a chart. First, we load the chart image we have just created in Excel to a slide. By clicking this button, we can convert this chart image to a PowerPoint chart object based on the embedded information. Once it becomes a chart object, we can further redesign it in PowerPoint. For example, we can use a different chart style, apply another color theme, or even change the underlying data of the chart. The last demo is a chart reader that can extract the information from chart images and read it aloud to people. In this demo, the chart reader application takes an embedded chart image as input, then extract the chart description from the image, and use text-to-speech technology to read it out to users.
This is a bar chart showing sales of different categories. You can see accessories has notably higher sales than others.
In conclusion, we have presented an embedding-based solution to unlock information locked in chart images. It guarantees the correctness and completeness of extracted data, and preserves the same chart reading experience as usual. Our experimental evaluation indicates that our embedded charts are well acceptable. Embedded data is robust to common operations on chart images, and also the embedding capacity is reasonably high. We have also demoed 2 applications. ChartM opens door to more potential applications around chart images.
Unfortunately, our speaker could not join us for this session, so we will dive straight into the next presentation, which is dataless sharing of interactive visualization, and the presentation will be led by Mohamed Raji.
Hello everyone, thank you for joining. In this presentation, I will be talking about dataless sharing of interactive visualization. I think we can all agree that sharing visualizations is extremely important in today's connected world. And whenever we want to do so, we often share visualizations through images or videos, which unfortunately limit the iterative thought process that comes with interaction. And whenever we want to include interaction, we have to do so by sharing the application and the entire data. And that causes its own types of issues. For example, sometimes the data or the application can be very large, which limits its shareability, especially through the web. And sometimes the software framework that is used for the visualization might not necessarily be available anymore, or might need hosting or maintenance. For example, Adobe Flash visualizations are now more difficult to use since Adobe Flash has been discontinued. And sometimes regulations and rules constrain the export of the data, but not necessarily the visualizations. In this work, we essentially present a new way of sharing interactive visualizations. Let's look at an example. So here we have the browser, just a normal browser, and within it we have an image of a Tableau that has opened an example dataset, the Superstore example dataset of Tableau. However, this is just an image of Tableau, but parts of this image are actually interactive. So the user can go in and click on the tabs and hierarchically go down and select parts of the map here. And even more complicated interactions are possible. For example, brushing or selection in this case, or discretized selection essentially, are possible. But Tableau doesn't exist here. These are just images as visual responses, essentially, of interacting with Tableau. And not just information visualization, but scientific visualization is also supported. For example, here we have the browser again and an image of ParaView within the browser. However, parts of this image are actually interactive. So the user can go in and use the slider on the left, for example, for clipping, or actually interact with the 3D data set in the middle and rotate it. So Loom essentially provides dataless but interactive objects that are very efficient. The examples that you saw in the previous slides are under 10 megabytes each, and it is very sustainable because the data and the application are no longer any requirement of this interactive experience anymore. It is also very controllable by the curator or the person that creates these objects for sharing. They can control what part of the application to capture and share and what parts not to. And essentially, Loom supports discrete interactions for explanatory visualizations mostly, compared to exploratory visualizations. And essentially, based on Bremer's taxonomy of visualization tasks, we support selection, navigation, arranging, and changing, but less so of filtering and aggregation, which depend on live user input at time of interaction. The main idea behind the Loom's approach is having a black box perspective to modeling visualization applications. What this essentially means is that we can look at a visualization as a user action goes in and visual responses come out, black box. Now, this is a simplistic view, of course, but it is also an application-agnostic view of visualizations that supports desktop or web-based visualizations or InfoVis or SciVis, and essentially models the input-output behavior. After that, the story becomes how can we emulate this functionality of capturing the actions and giving out the visual responses and store it, essentially. So let's look at how Loom objects are created. Everything starts by modeling interactions as what we call an action tree, which is essentially very similar to behavior trees in game design and are detailed in the paper. After interactions or possible interactions with the application are specified as an action tree, Loom then goes in and starts automatically interacting with the visualization application that we would like to capture and share. This interaction is done automatically, and essentially Loom does a complete parameter sweep of all the possible interactions based on the action tree and stores and saves the visual responses as screenshots along the way. the automatic interaction is done with low-level OS events like mouse clicks. The result of this is a Loom object, which includes the action tree and also a compressed video that includes the sequence of all the possible screenshots, essentially all the visual responses of the visualization. Here's an example of what that video might look like. It includes all of the possible visual responses, essentially. So what is an action tree, essentially? An action tree is semi-automatically specified by the user, and it's essentially a simplified UML similar to behavior trees. And later on, whenever we reconstruct the interactive experience in the browser for a Loom object, we convert this action tree to a state machine that models the interaction with the application. The action tree has a series of information within its nodes, but most importantly, every node has a unique ID that corresponds to the frame number that is the visual response to that action in the video. So let's look at an example of an action tree. On the left, we can see the Tableau example with two buttons on the bottom. Now, depending on, there's a decision for the user, and depending on which one of these buttons the user chooses, different visual responses can be shown to the user. This is captured in the action tree on the right, where from the root, the user can click on Overview, the tab Overview, or the Profits tab by clicking, and after that they are presented with several other visual elements that they can interact with. Specifying these interactions in the action tree is, as we mentioned earlier, is done through a semi-automatic manner. It is done through an application called LOA, which is Loom's overlay application. It is a semi-transparent user interface that we provide. On the right, we can see LOA on top of the Tableau example, and the user has selected the maps in the states in the map of the US as visual elements that can be interacted with. And this interface has been put on top of Tableau, essentially. LOA provides a set of tools that simplify and automate parts of this specification of the possible actions. For example, in this case, there is a magic wand capability where the user can use the magic wand and select the underlying visual element easily. Or there is also support for grid selection for cases where we have a grid of buttons or visual elements that we would like to hover or click on. In this case, for example, the user is selecting a 2x3 grid. Also, there is support for a smart selection, where the user can select an area and visually distinct elements are automatically selected by Loom through image processing. So later on, after the Loom object has been created, we can reconstruct this interactive experience in the browser for the end user that is using the Loom object. What happens there is that the Loom's viewer, which is a series of JavaScript libraries, essentially look at the action tree, and for each node they create a DOM element in the browser and create DOM event handlers that handle user actions. And based on the user action of the user, we essentially show the correct visual responses, the correct frames from the video as responses to the user. This logic of going from the action to the visual response is done by converting that action tree to a state machine that essentially models the behavior of the original visualization. Traveling to each state in this state machine displays the corresponding frame of the video. And there are a series of rules for the conversion from action tree to a state machine that are detailed in the paper. So we tested Loom with a series of applications from InfoVis and also SciVis. For example, on the right top-hand side, we can see a World Cup visualization from the New York Times that has been captured by Loom in the browser. And the size of that particular Loom object was about 5.5 megabytes for 628 different interactions. Or for a more involved and complicated example, we captured a pair view, a dataset in pair view, with 2 3D rotations. The size of that one was under 10 megabytes, 9.9 megabytes specifically, for about 1,000 number of interactions. Overall, in our tests, the kilobyte per interaction ratio was under 40. We also did an informal user study to see how much effort is needed to specify the action tree, essentially, as a curator. We had 3 participants that were computer science students, and they used Loom to capture parts of 3 visualizations, essentially. One thing we noticed was that the time it takes to specify the interactions does not necessarily correlate with the number of interactions, but does correlate with the number of targets in the application. For example, with a pair view Loom object with 2 3D rotations, that took about 3 minutes for 6 targets and about 1,000 interactions. To clarify here, the number of targets is different than the number of interactions. For example, one 3D rotation is one element or one target, essentially, but it can include many different interactions, many different rotations. One of the participants also mentioned that their skills in Photoshop helped them understand how to use Loa much easier. So in summary, Loom shows that it's possible to separate the interactive user experience from data and its application. And this enables a set of new application scenarios for essentially sharing data-intensive interactive visualization with very minimal resources through the web and across many, many platforms, essentially anywhere that supports a browser, regardless of whether the original visualization was web-based or not, or whether what the data size of that original visualization was. It also allows for archival and preserving interactive visualizations that might be more difficult to maintain later on, and also allows for a control on what is shared on a per interaction basis, essentially specifying this part of the application I would like the users to be able to interact with, and this part I do not like to. And we hope that this can have interesting applications in collaborative visualization, education, and data journalism. Thank you.
Thank you, Mohammed. And we already have quite a few questions popping up on the Discord channel. The first one is, what is the boundary for dataless? Isn't a scatter plot just a different encoding of the data from a CSV file?
Yeah, that's a really good question. But I think it also goes back to the distinction of a data set in rasterized media. And perhaps a better term here is data set-less sharing. That might be a better, more accurate terminology. But the idea is to eliminate the limitations that come with sharing the data set and not necessarily with rasterized media. One, for example, could be the growth in size that large data sets come with. But if you have some sort of video that is compressed in this way and is interactive, then that wouldn't occur. So I think it's that kind of distinction and that's playing there. Another aspect regarding that question, I think, is that Loom gives you control over what you can share and what you want to share. So it's less so of kind of like essentially extracting some sort of interaction and perhaps illegally pushing it somewhere or sharing it through the internet, but more so that you have actual control over what parts you are allowed to share and share those only.
And we have another question. So given that the selection of interactable areas seems to be image-based, how could you capture visualizations that are by themselves animated?
It's also a good question. So animation could be captured as is, as long as it's somehow finite. For example, if someone clicks on an area in a visualization, of course, Loom would need to have a plugin for it. It's extendable, so you would have to write a plugin. But Loom could then record that part of the animation for a specified amount of time and literally replay that later when the user interacts with that area in the visualization. But of course, in the example that the question had, for example, if we have some sort of flow animation that is just going on for a long time, that would not be easily feasible.
We have time for one more question. So if the image contains the data, but not in form of the traditional statistical graphics, which means it's not a scatter plot or bar chart, not a 3D scientific model neither, but the other representations like a storyline, a QR code, would it still work or remain interactive?
Model either, but the other representation like storyline QR code. Oh, I see. I think going back to Bremer's taxonomy of interaction, regardless of what types of visualizations we have, for example, if we have, let's say, a storyline visualization or something like that, it would still work with Loom as long as the types of interactions that are involved are the ones that we mentioned in the slides that were supported. So even parts of a whole other application that are not necessarily a visualization can be captured as long as those interactions are the only ones that are involved. For example, clicking or brushing sliders and such.
Perfect. Thank you, Mohammed. And this concludes our section. So I would thank all of our speakers once more, because I think this was a really interesting and very lively sessions. And also would like to give a big thank you to our fantastic technicians, and everything ran very smoothly. And also I want to thank you all for attending the session. We hope you keep the discussion live on the Discord channel or offline. And also I wish you to enjoy the rest of the conference. Thank you very much.
Druid.js is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Druid.js is a web tool using DR. You just need to import Druid.js, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the Xinke model is not easy to understand. We introduced the Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the Explainer, users can progressively explore the Xinke model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and the low-level underlying mathematical operations.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
In this study, we designed a system named Quadratic Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained data path extraction method, a river-based visualization, and a contribution analysis method.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
The recent COVID epidemic has triggered several different crises that are testing our civilization's potential for both coordination and cooperation. Data about infection rates and their growth has been the main source for public discussion and has inspired many visualization works. We propose a VA approach that incorporates a growth predictive model. This allows the correlation monitoring of the virus population development. We also can relate it to different government response events, as well as identify key dates.
In a visualization, laying out labels to data points needs to be done automatically with a fast labeling algorithm. We introduce Occupancy Bitmap. It's a data structure that helps the labeling algorithm to, first, quickly record the positions of existing marks and labels, and second, quickly detect overlapping of labels to the recorded positions.
Taylor coil flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Data lakes can contain millions of tables. Data portals have tools like keyword search to find data sets, but often researchers don't care about semantics, but rather structural metadata. Can I find a data set with many rows, few columns, and preferably a high number of unique values? Log Perspective visualizes structural properties based on the user's needs and helps researchers fish out data sets with appropriate structural properties.
In this presentation, we introduce a provenance library, Track, which makes implementing provenance in web-based tools easy. Track introduces a novel storage model for web-based provenance tracking and has an associated history visualization, which can be fully customized. Track also contains multiple ways to save and share individual states or entire sessions of an application and ensures that exported data is easy to analyze in interesting and unique ways.
General audience is likely to become distracted during the ever-changing animated visualization and reluctant to consume the entire animation. Informed by the role of foreshadowing that builds the expectation in film and literature, we formulate and apply visual foreshadowing on animated bar chart to improve its engagement. In addition, we implement a proof-of-concept authoring tool and conduct a user study to learn the efficacy of engagement enhancement of our approach.
DVR has always been from considerable interest to the scientific community. To this day, traditional desktop setups are the gold standard. However, what if we could utilize DVR in virtual reality? Now you think, VR and DVR are so computationally expensive, how is this even feasible? Come to my talk and we present you a straightforward solution to visualize volumetric datasets with high refresh rates on VR devices.
Evaluating alternative interpretations is an essential part of complex sense-making, but the resulting ambiguity is rarely considered in the design of visual analytic systems. Avalanche forecasters rely on sparse and human-produced data to assess avalanche hazards, often resulting in ambiguous interpretations. We used simple glyphs and unit visualizations to specifically consider and support ambiguity in the avalanche forecasters' sense-making processes.
Forensic investigation of file system metadata is a difficult and time-consuming task that requires deep expert knowledge. Following a user-centered design, we implemented an analytical tool to guide analysts during a security incident investigation. The evaluation proved that the tool could significantly improve the efficiency of disk exploration, even for less experienced analysts.
A dynamic graph models changing relationships between entities over time. In this work, we present multi-scale snapshots, a visual analytics approach to provide an overview of a dynamic graph at multiple temporal scales. The approach consists of 3 steps: creating multi-scale temporal summaries, applying graph embeddings, and the semi-automatic visual analysis. The combination of these steps lets us visually explore how temporal and structural properties affect the overall dynamic graph.
The ever-evolving landscape of malware detection and evasion creates a constant catch-up contest between the defenders and the adversaries. We created a system which submits and analyzes a malware sample with Cuckoo Sandbox and then animates the battle between the malware and the anti-malware system. The Gotter Evade 'em All system is a useful tool that uses a familiar concept based on Pokemon, allowing the understanding of malware evasive behavior to be more accessible.
Information about vulnerabilities helps defenders prioritize what they need to patch, but this information can be difficult to interpret. In this paper, we support interpretability using a focus and context approach to visualizing vulnerability data, including a clustering overview, plots that enable filtering based on severity, and explanations of text features and descriptions. We invite you to read our paper to learn more.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that lets users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
Tableau helps you see the stories in your data. It's designed to help you be smarter,